can think of a black hole as completely consuming the volume of space-time in its vicinity.
Although it may seem like black holes with their immense mass and power have always existed, they actually do have an origin.
Long ago, we didn't know if black holes would be common in the centers of galaxies with the help of the Hubble telescope, which has good, precise ways to look down in the center. Every galaxy we've had the capacity to check has revealed a black hole to us. Thus, we will extrapolate and assert that a black hole is a natural phenomenon in the center of all galaxies of the universe.
We're ready to delve into the structure of a black hole, an exploration that might reshape our comprehension of the cosmos. Join us on this journey as we seek answers to one of the most profound questions in astronomy.
On April 10, 2019, a groundbreaking moment in the history of astronomy occurred when the European Commission, in collaboration with the Event Horizon Telescope project, unveiled an image that had never been seen before. A remote galaxy located a staggering 53 million light-years away from Earth. This image focused on the heart of the distant galaxy M87 and revealed something truly remarkable. The very first image of a supermassive black hole. This historic unveiling provided tangible evidence of a celestial entity that had previously only existed as a concept in the realm of theoretical physics. The image allowed scientists to measure the black hole's mass with greater precision, confirming its existence and further aligning it with Albert Einstein's theory of relativity, which had predicted that black holes would exhibit a spherical shape. In the past, astronomers were uncertain about whether black holes were common in the centers of galaxies. However, with the aid of powerful instruments like the Hubble Space Telescope, which provides precise observations of the center of galaxies, astronomers have discovered black holes in every galaxy they've examined. This leads to the extrapolation that black holes are a natural phenomenon at the heart of all galaxies, fundamentally reshaping our understanding of the cosmos. But what exactly are black holes? These cosmic entities are extraordinary phenomena born from the dramatic demise of massive stars that have exhausted their nuclear fuel. When such stars experience a supernova explosion, their outer layers are violently ejected into space, while the core undergoes a gravitational collapse. If the core's mass is several times that of our Sun, gravity's overwhelming force causes it to implode. This implosion is so severe that it compresses the mass into an incredibly small volume, akin to squeezing a softball until it's as small as a grain of sand while retaining its original mass. This process leads to the formation of a black hole, a region where matter is concentrated so densely that it creates gravitational forces of immense strength. The key feature of black holes is their event horizon, a boundary beyond which nothing, not even light, can escape. Once something crosses this boundary and enters a black hole, it is trapped forever, a concept that defies our intuition about the universe. Black holes come in various sizes, with stellar black holes being a few times the mass of our Sun, and supermassive black holes having millions or even billions of times the Sun's mass. Scientists have long studied the indirect effects of black holes, gradually unraveling their intricate characteristics. However, one intriguing question has always persisted. What happens inside a black hole? To explore the structure and inner workings of black holes is to embark on a journey that could profoundly reshape our comprehension of the cosmos. As we delve deeper into the mysteries of black holes, we aim to answer one of the most profound questions in astronomy. What are black holes? Black holes are not just abstract cosmic phenomena. They have a direct connection to the states of matter and fundamental forces that govern the universe. One of the intriguing aspects of black holes is the phenomenon of electron degeneracy. This concept is related to the limits of matter compression and is rooted in the principles of quantum physics.
You're trying to cram electrons into the space of other electrons, and they don't allow that, all right, from quantum physics. They keep their own identity within the structure.
This state of extremely dense matter can be found in white dwarfs, which is the remaining core of a star like our Sun. Consider the massive space between an atom's nucleus and its electrons. If an atom were the size of a football stadium, the nucleus would be a tiny poppy seed at its center, and the stadium walls would represent the electron orbits. This fact was uncovered by J.J. Thomson. In his experiment, he shot particles at a thin layer of gold. What he found was that most of the particles zoomed straight through, as if there was nothing in their path.
The next morning, he is rumored to be afraid to step onto the floor, getting out of bed, that he might fall through it, because he alone knew how empty.
To understand electron degeneracy, consider the forces that hold atoms and molecules together, specifically the electromagnetic forces between electrons and atomic nuclei. These forces maintain the structure of ordinary matter, such as rocks. However, when matter is subjected to extreme pressure, such as in the core of a massive star during its collapse, it can push electrons closer together. This results in a situation called electron degeneracy, where electrons resist being squeezed further due to the Pauli exclusion principle of quantum physics, which states that no two electrons can occupy the same quantum state. This state of extremely dense matter can be found in white dwarfs, which are the remnants of stars like our Sun. To put the density of neutron stars, the next stage of matter compression, into perspective, imagine taking a herd of 300 billion elephants and cramming them into a thimble. This level of density characterizes neutron stars, which are incredibly dense celestial bodies composed primarily of neutrons. Neutron star matter is so dense that it weighs as much as a mountain per teaspoonful, and it possesses gravitational forces that can bend light. Neutron stars that rotate rapidly emit strong magnetic fields, creating pulsars. The discovery of pulsars, made by Anthony Hewish in the 1970s, earned him a Nobel Prize. As we progress in understanding the compression of matter, we inevitably reach a point where it cannot be compressed any further without becoming a black hole. Black holes come in various types, each with distinct characteristics. The most common type is the stellar black hole, which forms when a massive star exhausts its nuclear fuel and undergoes gravitational collapse, shrinking its mass into a tiny volume. These stellar black holes can be several times the mass of our Sun but are incredibly small, with event horizons just a few kilometers across. Intermediate mass black holes, whose exact formation process is still debated, have thousands to tens of thousands of times the Sun's mass and are denser than stellar black holes. At the upper end of the scale, we find supermassive black holes, which inhabit the centers of most galaxies, including our Milky Way. The formation of supermassive black holes remains a mystery, with one theory suggesting they grow from smaller black holes by continuously accreting matter from their surroundings. Another intriguing variation is charged black holes, which possess an electric charge. There are two main types: Reissner-Nordstrom black holes, which carry a charge but do not spin, and Kerr-Newman black holes, which both carry a charge and spin. These charged black holes exhibit unique phenomena, such as frame dragging, where the spinning black hole twists the surrounding spacetime. One critical concept often associated with black holes is that of dark matter. Dark matter is a unique form of matter that outweighs visible matter in the universe, earning its name because it does not interact with light or other forms of electromagnetic radiation. While dark matter itself is not typically considered the direct source of black hole formation, it plays a pivotal role in shaping the distribution of matter in the universe. Some theories suggest that dark matter acts as a gravitational scaffold around which galaxies form, creating conditions conducive to the birth of black holes. Moreover, there is speculation that primordial black holes could be a component of dark matter. If this theory holds true, these black holes would have influenced the dynamics of the early universe through their gravitational pull, potentially leading to the formation of more stars and galaxies. This intriguing possibility suggests that black holes and dark matter could be interconnected on a fundamental level. In our exploration of black holes, we encounter a fascinating interplay between the forces of the cosmos and the counterintuitive rules of the quantum world. One of the most remarkable phenomena that bridges these realms is Hawking radiation, a theory proposed by Stephen Hawking. Hawking radiation offers a glimpse into the quantum properties of black holes. It suggests that matter and antimatter particles can spontaneously appear near the event horizon of a black hole. In normal circumstances, these particles would annihilate each other and disappear. However, if one of these particles falls into the black hole while its antimatter counterpart escapes, it results in Hawking radiation, the release of energy and particles from the black hole. This theory implies that black holes are not completely inescapable, as they slowly lose mass due to Hawking radiation. This phenomenon addresses a long-standing question in physics. Can anything escape a black hole, given that nothing can move faster than the speed of light? Hawking radiation provides a compelling explanation for how black holes can emit radiation and lose mass over time. Thank you for watching another episode of Space Odyssey. While you are still here, don't forget to like and subscribe.